the background to grind my coffee.
Our final topic in the chapter on game theory will cover sequential games. Now, if we had a full course on game theory, the majority of the course would be spent on sequential games, which are more realistic to the real world because they incorporate an element of time or a sequence of moves. So we did briefly see a sequential game in the duopoly problems. We called it the Stackelberg duopoly, where you had a leader firm that moved first, then the second firm which observed this quantity choice and set their own quantity choice. So again, in sequential games, you have this sequence of moves, and then you will have players in the game which can see where in the game they are. So in sequential games, players' strategies have to include complete courses of action throughout the game. So basically we're saying the player can see where they are in the game, and they must incorporate an action for each possible place that they are in the game. So let's consider this coordination game again. Player one chooses Harry Potter or Avengers, but this time, instead of a simultaneous and non-cooperative game, there will be a sequential game. So in this case, player two can see whether player one has put Harry Potter or Avengers into the DVD player. All right, so in this case, player two has two information sets. If player one chose Harry Potter, player two is able to see that and knows that they're right here. If player one chose Avengers, player two can see that, knows they're right here. So player one has one information set. Their strategy set then is relatively easy. Where did I define strategy sets? Down here at the bottom. So what's player one's strategy set going to be? They're just picking at the beginning of the game. They choose Harry Potter or Avengers. So Harry Potter or Avengers is the strategy set. But strategy sets become a little bit more complex to define when people can observe previous moves in the game. So player two chooses Harry Potter or Avengers, but they also know whether they're here or here. And to be complete, a strategy for player two must specify what they will do if player one chose Harry Potter and what they will do if player one chose Avengers. So what are the possibilities? I've just listed them out here and then written them in shorthand. So the possibilities for player two would be, if player one chose Harry Potter, pick Harry Potter, or also pick Harry Potter if player one chose Avengers. So we'll list that as HH, once again, meaning if player one chose Harry Potter, choose Harry Potter. If I see that player one chose Avengers, I still choose Harry Potter. Right, another possible strategy would be AA. If I see that player one chose Harry Potter, player two picks Avengers. If player two sees player one has chosen Avengers, pick Avengers. All right, what else could we have? We could have Harry Potter if Harry Potter, Avengers if Avengers. So if player one chose Harry Potter, player two chooses Harry Potter. If Avengers, then Avengers. That would be Harry Potter if Harry Potter, or Harry Potter if we're on this side, Avengers if we're on this side. And then the last possible strategy would be, if we're on this side, choose Avengers, and if we're on this side, choose Harry Potter. So do the opposite of what the opponent did. Avengers if Harry Potter if Avengers. Right, so you should be reading these strategies as what player two does if they're on the left branch, and what player two does if they're on the right branch. So to solve these types of problems, we will use a solution method that we call sequential rationality. And again, we really won't have time to get deep into the detail of these sequential games. They become really interesting. But we will study just in general the basic solution method that would be used to solve these types of games. So with sequential rationality, or another name for it is called backwards induction, we start with the final decisions in the game and work backwards. So what are the final decisions of the game? There'll be player 2's decision, either here or here. So if player 2 knows that player 1 has chosen Harry Potter, or in other words, they know they're right here, what is player 2 going to do? They get 2 for Harry Potter or 1 for Avengers and should choose Harry Potter. All right, so the sequentially rational strategy would be Harry Potter if Harry Potter. What about Avengers? If player 1 has chosen Avengers, what should player 2 do? Well, player 2 would get 1 for choosing Harry Potter in this case, or 3 for choosing Avengers. So the sequentially rational strategy is to choose Avengers in response to Avengers. In other words, player 2's sequentially rational strategy is Harry Potter if Harry Potter, Avengers if Avengers, which for shorthand we listed as HA. Harry Potter if I'm on this branch, H. Avengers if I'm on this branch, A. Right? What about player 1? Player 1 knows then if player 2 is behaving sequentially rational, player 2 will choose Harry Potter if Harry Potter and Avengers if Avengers. So what is player 1's sequentially rational decision? They would get then 3 for Harry Potter or 2 for Avengers, thus chooses Harry Potter. So we can write out the sequentially rational Nash equilibrium of this game as H for player 1, or player 1 choosing Harry Potter, player 2 choosing Harry Potter if player 1 chose Harry Potter, but they would have chose Avengers if player 1 had chosen Avengers. All right, just one more brief example with backwards induction. We call this one the pirate's treasure problem. Suppose you've got N pirates aboard a ship. Let's just choose N equals 5. The pirates are ordered by rank A, B, C, D, E, with A being the captain. The pirates have 100 treasure to split and will do so democratically as follows. Pirate A first proposes a split of the treasure. All pirates then vote on that split. If the vote passes, the game ends, and if not, the pirate who proposed is thrown overboard and the next pirate proposes a split. Also, any vote resulting in a tie will pass. So the question we're asking here is, what is the largest share of treasure that Pirate A, the captain, can vote themselves or propose themselves and still live? So it does end up being true that Pirate A could propose an equal split and the vote should pass and everyone would live, but that turns out not to be the best Pirate A can do. To illustrate this, let's use backwards induction, sequential rationality. So suppose there's one pirate remaining. We get all the way to the end, everybody's thrown overboard. This is a simple case, E takes all the treasure. With 2 pirates remaining, D would propose a split. What split would they propose? 100 for D and 0 for E. And because a tied vote will pass, D votes for this split, E would not, but it still passes. What about then if there were 3 pirates left? Here's where things start to get a little bit interesting as far as the logic goes. So with 3 pirates remaining, now it's C proposing the split. And C knows that if they're thrown overboard, D is going to get all the treasure. So in that case, E would be willing to vote for a split where E gets 1 treasure and C takes the rest. Right? E is going to vote for this because they know if it reaches the next stage, E gets 0 treasure. So C votes for this, E votes for this, it passes. All right, keep on going backwards. What if there's 4 pirates left? This time B proposes a split. B knows that if they're thrown overboard, C is getting nothing. D will get nothing. C will get 99, D gets 0, E gets 1. So if B is allowed to propose, they should offer 1 treasure to this person, Pirate D. Pirate D will vote for it. So 99 for B, 0 for C and E, and 1 for D. D votes yes because they know if B is thrown overboard, they get 0 treasure. So this one passes a 2-2 tie. Finally, working back to the case where we have 5 pirates. A is the captain and proposing. A knows that if they're thrown overboard, C and E will both end up with 0. So A can propose a split where A gets 98, C gets 1, E gets 1. C and E should both vote for this because they get 0 in the next round. And so using backwards induction, the maximum amount of treasure Pirate A can claim is 98. All right, so just one kind of more complicated example of a backwards induction problem. So what about other types of games that happen over time? We could have repeated games. And if we have a game which is repeated, it can be repeated either finitely or infinitely. If it's repeated finitely, we once again use the backwards induction or sequential rationality method to study the solution. So consider this prisoner's dilemma game. This is an additional formulation of the prisoner's dilemma, but you should verify that defect is the Nash equilibrium of this game, and it's worse off than cooperate. So defect is the dominant strategy solution. So simply stated, what we're going to say is that if this game were repeated finitely, cooperation would not be possible without changing the payoffs. Why? Suppose the game lasts n rounds and everybody knows that how many rounds it will last. Now, suppose we're now in the final round. What's going to be the equilibrium of this game? Each player, knowing it's the final round, has incentive to defect. So DD. Well, then what about in the previous round? In the previous round, everybody knows everybody's going DD in the final round. That makes the n-1th round the final round, and everybody picks DD once again. So we say in general, in finitely repeated games, cooperation is not possible, but that it is possible in what we call infinitely repeated games. So infinitely repeated games, or games that are repeated enough times that players don't know exactly how many rounds there are or when the final round will occur, make cooperation possible. And this is, again, if we had a full class on game theory, we would spend a number of weeks. So it would probably be at least one full midterm on these sorts of repeated games or infinitely repeated games in which cooperation is possible. We won't have time for it, but I have posted kind of an older documentary from Richard Dawkins here. It's an interesting watch. It's from like 1985 or something, so the graphics aren't great on that. But if you're interested in game theory, I think this is an interesting, it's only like 45, 50 minutes. And it basically just talks about how these kinds of simple 2x2 or prisoner's dilemma or simple coordination games have been applied in nature between humans. So kind of a more real world sense of where we start using game theory to analyze decision. So I would have loved to be able to, take one class period and hang out and watch this documentary. It can be done in one day, but of course we won't have time for it. So, over break when you're hanging out, feel free to give this a watch. All right, what it basically talks about, just kind of summarizing, is that in infinitely repeated games, there are possibilities for cooperative strategies. So again, referring to this prisoner's dilemma type of games, a couple of strategies which ultimately result in cooperation would be one we call tit for tat. And in a tit for tat strategy, you just repeat whatever your opponent played in the last round. So that would be cooperate in the first round, and then in each subsequent round, cooperate if your opponent cooperated in the last round, and defect if your opponent defected in the last round. So if two tit for tatters met, they would start cooperate and then play cooperate in each subsequent round. So that would be one cooperative possibility. Another cooperative type of strategy, although it doesn't sound like it, is a Grim Reaper policy. So sometimes this is how relationships work, but you cooperate in the first round, and then if in any round your opponent defects, then you choose defect in all subsequent rounds. But if two Grim Reapers met, then they would cooperate in the first round, and because each had cooperated in the previous round, they would cooperate in all subsequent rounds. All right, so again, this documentary I've posted again just talks about basically how these types of cooperative strategies evolve in nature and between people over time in these kind of simple game frameworks. All right, so that's pretty much the end of the material for the class. I've enjoyed it, and let me know if you have any questions.